talk about liquid crystal droplets, and colloids, basic properties. And Oleg has been exceptionally brave. He flew through the night and just arrived here just as he got off the plane. So I think we need to salute him for...
Thank you. It was just very good time to prepare the talk. So, I'll be talking about little bits of things with liquid crystals that were of interest to me personally and to colleagues of mine. And this will be revolving around things that are round, liquid crystal droplets and colloidal particles in liquid crystals. So I would like to start with some very basic things that describe the behavior of liquid crystals in confined volumes. And those things are elasticity, and I'll be speaking in terms of the director field, and surface anchoring, or anisotropy of the interfacial tension. I'll briefly discuss what happens when you disperse a liquid crystal in the form of droplet, either in a foreign fluid or in its own melt. Then I will talk about LC squared. It's kind of liquid crystals with two dimensions, as you would see. Those are so-called lyotropic harmonic liquid crystals, and we will see some unusual properties that they have as compared to thermotropic liquid crystals. And the last part will be about colloidal particles in liquid crystals, statics, and dynamics. So, as Tim explained, the liquid crystals, the simplest phase in them, the so-called nematic, is just a fluid in which you have orientational order of anisotropic molecules or aggregates of molecules. And we call this direction of preferential orientation the director. And in a uniaxial nematic phase, the director is also the optic axis. This is what makes liquid crystal textures so unique, and this is why we can reconstruct the director field by observing the liquid crystals under the microscope. For us, it's not that important probably to deal with the reorientation of this anisotropic fluid in the external electric field or magnetic field. The two most important things will be the concept of elasticity and anisotropy of surface tension. So elasticity deals with the simple fact that whenever you want to misalign the director so that it's not pointing into some direction that is constantly spaced, whenever you would like to make a distortion like a splay with my fingers, you have to perform some work because the molecules would like to be parallel to each other. And according to the Frank-Ozin-Zoher theory that Tim described, you have the coefficient k, or Frank constant, that characterizes the kind of amplitude of this work. And then this work also would depend on the degree by which you realign the director. And in order of magnitude, the density of elastic energy is something that scales with the characteristic size of distortions as 1 over r squared. And when you take the integral over the distorted region that is of typical size L, you come up with an estimate that the elastic energy grows linearly with the size of the distorted volume. Now, surface anchoring is the result of anisotropic molecular interactions. The bulk interactions lead to the formation of the director, but at the surface, the anisotropy of molecular interactions lead to some preferential orientation of the molecules at this substrate. And this orientation might be tangential to the interface, or it might be perpendicular or tilted. By the way, most of the examples that would follow are about the director field that is tangential, strictly tangential to the interface, or perpendicular. So whenever you would like to change this orientation at the surface, you again need to spend some to perform some work. And from the dimensional analysis, you would realize that this energy should be proportional to some coefficient, which is called the surface anchoring coefficient, and is a function of the properties of the substrate and the liquid crystal, and the area of the interface over which you would like to realign the director. What is interesting is that K over W has the dimension of length, and it just happens that for so-called thermotropic liquid crystals, those are formed by pure compounds that are heated from the crystalline phase. So for the thermotropic liquid crystals, this length is in the range between about 0.1 and 1 micrometer. It's a kind of surprising result, and it immediately brings the liquid crystals in the domain of colloidal science to some extent, as you would see later. So now imagine that you have some abstract volume of a liquid crystal embedded in the medium that is different from this liquid crystal. So there is an interface, and you would like to know what would be the equilibrium state of this volume in terms of the shape and in terms of the interior, which contains the molecules that normally would like to be parallel to each other. So you have to minimize the surface energy that is anisotropic and the elastic energy of the distortions. And there are well-established approaches to characterize both. For the surface energy, you would like to have something that is not dependent on the orientation of the director, some bare surface tension, if you wish, that tells you that the surface would like to shrink to become minimum for a given volume, provided you don't have anisotropic properties at this surface. And then there should be some function of the angle between the director and the normal to the interface. And it turns out that in the simplest approximation, you can just use this first term that is proportional to cosine of the angle squared. But as was shown by Tim and his colleagues, for many cases, for example, when you observe or describe the surface anchoring transition of the first order, that's when the preferred orientation of the director at the surface changes from, let's say, tangential to normal. You need at least two different terms in this free energy density. And in terms of experimental parameters, Fayeti and his colleagues measured the bare surface tension for the typical thermotropic liquid crystal in contact with its own melt, and found that this is a quantity that is 10 to the minus 5 in System International. And it's a very good order of magnitude for many other liquid crystals that when you characterize the interface between the isotopic melt and the liquid crystal. In the same work, Fayeti also measured the coefficient of surface anchoring and found it to be about 10, 20 times weaker than the surface tension. So you can say that the interface between the nematic and the isotopic melt is only weakly anisotropic. You have the ratio of the anchoring strength to the bare tension on the order of 10% or 1%. Now the elasticity, we can use the Landau-Dejean approach, the Q-tensor formalism, and we can also use the Frank expression written here that contains the three bulk terms and three surface-like terms, and I think there will be talks about these things. I would like just to mention that in many problems, people just restrict their attention to these three bulk terms. K to 4 becomes important when the topology of the volume changes, or when you introduce topological defects. Blue phases are a good example of this situation. But in most of our examples, we are not dealing with surface-like terms in this presentation. So from the estimates above, yeah, by the way, I've forgotten to mention that experimentally, the order of magnitude of K is 10 piconewton, and you can find an estimate in the Dejean's book for K as simply the temperature of room temperature at which many liquid crystal melts divided by the characteristic size of the molecule. That would give you about 10 piconewtons. So from these estimates, we see that if the volume is supramicrometer, then the surface tension is much larger than the elastic energy. So you would expect the sphere to be the droplet to be a sphere. And another thing is that the surface anchoring energy is also larger than the elastic energy. So you would expect the director to try to satisfy the boundary conditions. And since the volume is typically closed, it's a sphere, that means that you should obey the differential geometry theorems, Poincaré and Stokes, and that means that your vector field, or director field, must contain a certain number of topological defects. And those are simple examples, so you can buy, if you are working for an academic institution, you can buy the liquid crystal. It turns out you cannot buy it when you are working from home. So you can buy this commercially available mixture and melt it and try to catch the temperature really close to the phase transition. And then if you're lucky, you would observe the droplets, big droplets of the nematic floating in the isotropic melt. This isotropic melt looks like black under a polarizing microscope with two crossed polarizers. And what you see is that in each droplet, there are some defects. You might see equatorial ring, and then there are some defects at the poles. On the right-hand side, it's a more clear image of a similar situation, but here, instead of the melt, you have glycerol that helps to form very nicely shaped spheres of a nematic liquid crystal. And you might see that in this image number B, you have equatorial disconations and two-point defects at the surfaces. Then you can play with the chemical composition or with the temperature of this system, and by changing the temperature, you can change the orientation, the equilibrium orientation of the director at the surface. And at high temperature, you can make the director being tangential, and in that case, you observe only two defects. And then as you change the temperature, you go to the situation when the director is perpendicular to the interface. And down the road, you see all the intermediate states with different sets of defects, disconations, and point defects. It simply tells you that in droplets that are of size larger than 1 micrometer, you have the topological defects inside each and every droplet that simply satisfy the surface anchoring at the liquid crystal isotropic fluid interface. So, of course, each and every rule has some exceptions, and this is a peculiar case of a phase transition between the cholestatic, which is a chiral nematic, and the smectic phase. And again, the previous lecture was discussing these two phases. So you start at high temperature with the cholestatic, and then you end at low temperature with the smectic. And you immediately see some strange thing happening. At the top, you started the experiment with 2 droplets, and at the bottom, the outcome is 3 droplets. And there was no kind of mechanical perturbation of the system, except the fact that the temperature was reduced from 84 degrees to 82. So what happened here was some strange transitional dynamics. When the temperature was lowered, the cholestatic apparently started to increase its pitch, and the droplets suddenly lost their spherical shapes. It was to us as if the surface tension became negative or close to 0, and then the nematic phase nucleated at the sharp ends of these elongated forms, and the smectic phase, of course, by itself wants to form round pieces of the liquid crystal, and since they form at different locations, you have a dynamics that leads to that breaks the original droplets and produces smaller droplets in the system. Of course, if you will do this many times, you wouldn't increase the number of droplets to infinity. They would coalesce and restore themselves. But what was interesting here is that at that time, and that was very long time ago, we considered the interface between the smectic and the cholestatic liquid crystal, and just drawing the analogy with the boundary between a normal metal and a superconductor, we suggested that probably this interface between the cholestatic and smectic might have a negative surface tension. And 2 years ago, and that was, of course, associated with behavior that is very similar to the type 2 superconductors. And 2 years after that, Ren and Lubezki proposed a theory that predicted the very peculiar case of bulk arrangement of liquid crystals, in which the cholesteric order and smectic orders coexist. And some 2 years after that, Goodby and his colleagues discovered the new phase that is the analog of the type 2 superconductors. Unfortunately, we didn't do much on the surface tension of this phase since that time, but it's just an example of how non-trivial the surface phenomena might be in liquid crystals. So I would like just to say that nowadays there is some interest to explore the droplets of liquid crystals from the point of view of using them as topological tests of the existence of new phases with background nematic type. One of those new phases is the so-called biaxial nematic phase. So you can imagine molecules not being just rod-like or disc-like. You can imagine them being box-like. And if you deal with boxes, then not only the long axis of boxes can align, but also the short axis of boxes can align parallel to each other. And that would be a biaxial nematic phase. And the symmetry of the phase dictates what types of defects you can produce in this phase. And if you consider the particular case of the spherical confinement, that you would realize that you cannot, for example, have the point defect in the center, because if you have the radial director, then the second director will form spherical surfaces. And you know that if you have a sphere and the vector field is defined on this sphere by Poincaré theorem, you cannot have a smooth vector field. You must have 2 poles or one defect that represents a junction of these 2 poles. So this particular texture would be impossible, and bipolar texture would also be impossible, because if you have the director that is tangential to the interface, then the secondary director would form a disclination, that line defect that connects the 2-point defects along the axis. And so it appears that the only, at least from the topological point of view, the only possible configuration for a biaxial nematic would be this so-called Budjum with 4 pi circulation of the secondary directors around it. And we were trying to test different candidates for the biaxial phase in spherical geometries, and so far we cannot find any kind of topological confirmation that these candidates form a biaxial nematic phase. Whatever you observe is always behaving as if it were a uniaxial nematic phase. There is a very interesting recent work by a number of groups. Here I just refer to the group from Ireland, Dr. Veitch, and a group from Scotland, Corey Imrie. They synthesized nematic molecules that represent just dimers. So it's a standard liquid crystal molecule like many of those that Tim was showing. But now the 2 of them, 2 identical molecules, are being connected by a flexible bridge. And it turns out that you have very unusual textures in this case. By decreasing the temperature in this particular case, you go from a standard texture of a nematic liquid crystal to something that looks, to those who studied liquid crystals, something that looks like a smectic. Those ellipses are so-called focal conic domains, and they occur only in systems in which you have some periodicity. And this periodicity wants to preserve itself despite the fact that the liquid crystal is curved in space. But what is interesting is that X-ray shows no traces of molecular smecticity or molecular periodicity. And it's a peculiar case of a nematic phase that has some elements that are periodic, but this periodicity is apparently not at the molecular scale. So I don't know whether there is a clear understanding of this phase. So I just briefly considered the droplets of liquid crystals. In thermotropic liquid crystals, we expect that for surface tension, for anchoring energy, and for the elastic energy of a typical droplet that is larger than 1 micrometer, you expect the following relationship. So the droplets are round, and they contain a certain number of topological defects in them. There are some interesting exceptions from this case, such as droplets in the cholesteric to smectic phase transition. And besides the practical applications, by the way, that I failed to mention, droplets of liquid crystals have been used in polymer dispersed systems, and you can use them as a kind of electrically switchable fog. You apply electric field, you realign the liquid crystal droplets, and the transparency of this polymer dispersed system changes as a result of the applied electric field. But you can also use them for tests of the existence of the biaxial phase, and who knows, probably also the X phase. The future directions are that we know very little how the surface tension of the thermotropic liquid crystals would change if, for example, you would add surfactants to the interface, or if instead of the isotropic melt or just the regular fluid such as glycerin, you would use something different. For example, a lyotropic liquid crystal in mixture with a thermotropic liquid crystal. I know that Peter Collins at Swarthmore College did experiments of this type. I don't know whether they have been published or not. The next story is about a liquid crystal that is very different from the thermotropic liquid crystal. So it's the class of lyotropic liquid crystals that exist when you disperse the anisometric molecules or aggregates of molecules in some solvent. And this solvent is typically water. And on the left-hand side, I show the tobacco mosaic virus in water. It's a low concentrated dispersion, so it doesn't show any long-range order. But as was shown by Onsager, when you are dealing with the dispersion of long rods and you increase the concentration of these rods, eventually the system would face the dilemma either to remain misaligned in terms of orientation of these rods and thus maximize the orientational entropy at the expense of hindering the translational motion. You see, if I increase the concentration of these rods, they cannot move that freely because they start to bounce into each other. And so the resolution of this restriction in translational freedom might be achieved by realigning the molecules along one direction. You lose the orientational entropy, but you gain the freedom to move the rods around. And this is the theory of the lyotropic nematic liquid crystal. For materials like this, there are theories that would predict you that the surface tension should be much smaller than in the thermotropic liquid crystal. The models would tell you that in order of magnitude, the interfacial tension between the isotropic phase of the lyotropic system and the nematic phase would be something like Boltzmann temperature divided by the size of the aggregates, which is L is the length and D is the diameter. The particular case of tobacco mosaic virus is such that L is on the order of many micrometers, and D is tens of nanometers. So these things are much bigger than individual molecules in thermotropic liquid crystals, which are, roughly speaking, a few nanometers long and half a nanometer, 1 nanometer wide. So you expect that sigma will be much smaller than in the case of thermotropic liquid crystals. And this is not a theory, it's just the experimental fact. People estimated the anchoring for lyotropic liquid crystals, and they concluded that the order of magnitude is something like 10 to the minus 5. So if you compare these two things, you would immediately realize that contrary to the case of thermotropic liquid crystals, here surface anchoring is expected to be much larger than the surface tension. And in fact, the very first observations of lyotropic liquid crystals by Bernal and Fankuchen demonstrated that the new phase, the nematic phase, appears from the isotropic melt not as round spherical formations, but as very elongated entities that were called tactoids. And tactoids signal that there is a much more interesting relationship between the surface tension, surface anchoring, and elastic energy. By the way, typically the elastic constants in lyotropics are of the same order of magnitude as in the thermotropic liquid crystals, between 1 and 10 piconewtons, but of course there are exceptions. So the lyotropic chromonic liquid crystals are yet another twist in the story of lyotropic systems. Here you have aggregates as the built-in units of the nematic phase, and these aggregates are not fixed. If you compare this material to the tobacco mosaic virus, in the virus case, each particle is a covalently bound entity that is very hard to break, and you change the temperature a little bit, nothing happens to the virus. In this case, the molecules are disc-like to begin with, and when you put them in water, they simply would like to hide their hydrophobic faces from water, and that leads to non-covalent aggregation that creates an elongated domain. So the forces between the faces of molecules, again, are not covalent forces, so they are very weak, few thermal energies. So if you change the energy, if you change the temperature, the thermal fluctuations will easily break the aggregates. And still, if you have not very high temperature and if you have enough of those molecules, the elongated aggregates would tend to form a nematic liquid crystal. Those are examples of chromonic molecules. And here you see that some of them are dyes, like this so-called sunset yellow. It's used in food. Some of them represent drugs, and this so-called disodium chromoglycate is known in its pure form as an anti-asthmatic drug. So it's a very broad family of materials, and even DNA can be put into the class of chromonic lyotropic liquid crystals. So, but if you just think in general terms and compare what's the difference between the LC squared or chromonics and the rest of liquid crystals, you would realize that if you compare them with the Onsager model, then in the Onsager model, the only thing that changes the phases is concentration of particles. The system is not dependent on temperature because it's just the competition of two entropy terms. So in the case of normal liquid crystal of thermotropic type, you don't change concentration because concentration is already 100%. It's all one material. You change the temperature, and whatever you do with temperature, it doesn't change the shape of the molecules. But in the case of chromonics, you have both temperature and concentration that modifies the order and modifies the very built-in units from which this phase is constructed. And on the right-hand side, you see the phase diagram. N is the nematic phase, and you see that you can change the concentration of the molecules when you increase. This nematic phase is being replaced by the so-called columnar phase. And you can also cause phase transitions by changing temperature. When you increase the temperature, the aggregates break, they become shorter, and then you have simply a different Onsager model that at some temperature becomes not capable of forming the nematic phase simply because the aggregates are too short to form a nematic. So the first question is how these properties will affect the elasticity of the nematic phase. And recently we did the experiment based on the magnetic Fredericks effect. This is the effect that was described this morning. You apply magnetic field, and you cause the liquid crystal to realign. And then, since you know the magnetic field, you measure the optical response of the liquid crystal. You can extract the force with which the liquid crystal resists this realignment, and that would give you some idea about the elastic constant. Not some idea, just it gives you a very accurate measurement of the elastic constants. And here you see an example for the elastic constant of splay, twist, and bend. Those are three bulk distortions of the director. They're of the same order of 10 piconewton. The only thing of interest is probably at this stage is that K2, the twist elastic constant, is much smaller than the splay and the band constants. And then if you continue the measurements for different temperatures and for different concentrations, you can plot how, for example, the ratio of the splay constant to band constant changes with temperature. And you see a behavior that is rather unusual from the point of view of Lick crystals of thermotropic type. In Lick crystals of thermotropic types, K1 and K3 converge to the same value more or less as the temperature is increased, and typically K3 remains larger than K1. In our case, the elastic constant of splay, K1, decreases much faster than the elastic constant of band. And since we remember that as a function of temperature, we might be dealing with different lengths of the aggregates, it is tempting to consider what might the lengths of aggregates bring to the behavior of elastic constants. So K3 is the constant that is associated with this type of director distortion shown as an arc there. And if you imagine the aggregates being subjected to such type of distortion, then it's clear that it's the elasticity of each and every aggregate against bending that should be involved. And there is a theory that explains the K3 in terms of persistent lengths of the chain or of the aggregate. And as you change the temperature, it doesn't look like this quantity needs to change much, so we'll just get this estimate as it is. K1 is a somewhat different beast. This is the deformation of splay, and you can see even from this image with my fingers that if I would like to create splay, then I need to fill the empty spaces between the fingers, and that means I need to bring the ends of the other molecules to keep the density of the material intact whenever I want to create the splay deformation. So as shown by Bob Mayer, K1 should be proportional to the length of the aggregates. If I have infinitely long, say, polymer chains, then it's very difficult to create splay because I simply wouldn't have free ends to fill these empty places. So from this simple consideration, it looks like K1 over K3, the ratio that we measured experimentally here, should be proportional to the ratio of two characteristic lengths. One is the contour length of the aggregate, and another one is the persistent length that shows you the rigidity of the aggregates towards bending. And again, we know very little about the behavior of the persistent length and the contour length. As I mentioned, whenever you change the temperature or concentration, you expect to change the length of the aggregates, but there is no theory that would clearly predict how that would happen. And here we just used the approaches developed for so-called worm-like micelles, approximate theories that allowed us to estimate the average length of the aggregates in the isotropic phase and in the nematic phase as a function of energy E that is the sticking energy of the two molecules, the energy with which they are kept together in the aggregate. Also as a function of the concentration of chromonic molecules, the diameter of aggregates, and the persistent lengths here. So the most important feature probably is that the dependency on the temperature of the system is very strong. It's an exponential dependency, and it comes again from the entropy of molecules in solution. And when you estimate the ratio of two elastic constants such as K1 to K3, you come up with the expression that tells you that as a function of temperature, it should drop down rather strongly because K1 is associated with the contour length of the aggregates, and K3 remains practically constant since it depends on the persistent length of the molecule. of the aggregate. So I would like to conclude here that even for the simple case of basic elasticity of chromonic crystals, we know very little about those materials, and these experimental results are the only results that are currently available for elastic properties of chromonics. So, but let's just move to the behavior of chromonics in phase transition. So here you see something that is reminiscent of Bernal and Fanquichin experiments. When you change the temperature and the nematic phase appears from the isotropic melt, you might see that the nuclei are of elongated shape. If the concentration of the material is high, then not only you observe tectoids, but sometimes you observe toroidal nuclei. Here in the center you have the isotropic phase, so it's like a little toroid that is floating in the isotropic phase, and it's happy because the director is tangential to the interface, and the only type of distortions that you have here are distortions of band. There is no splay, so apparently the aggregates are becoming very long or infinitely long, and they're just circulating around this hole in the toroidal nuclei. So we decided to explore in details what are the director structures of tectoids. And first, it appeared that it's just a simple exercise. We are repeating what Bernal already knew, that the material has a director that joins these two opposite poles. But unlike other studies, we had the ability to see the vertical cross-section of the cells. And what we realized with some surprise was that all these tectoids, despite the fact that they look like nicely shaped, they're all located at the interfaces. They're all having their base at the glass. And so they're not actually axially symmetric formations in our system. They represent rather complex shapes that are attached to the glass boundaries. Another interesting thing was that by observing them between the two cross polarizers, we realized that if the axis of the tectoid is oriented parallel to one of the polarizers, it's not going to become dark. You see that when the analyzer and polarizers are perpendicular to each other and one of them is parallel to this axis, the central part of the tectoid is bright. To those who know a little bit about propagation of polarized light, it means that the polarization plane of light has been turned to some, either to the left or to the right, and we can establish this by observing the tectoids with differently crossed polarizer and analyzer. And what we realize is that the tectoids are in fact twisted. Half of them twists the director to the right, half of them twist the director to the left. And the surprising fact is that this chirality this broken symmetry of chirality occurs in a system that doesn't have any chiral molecules. It's not the derivative of cholesterol with chiral centers in each and every molecule. The system doesn't have any chiral molecules at all. What it takes is just the anisotropy of the elastic constants and confinement in the form of tectoids to produce this chiral symmetry breaking. And here is a very simple explanation how this is happening. If you have a liquid crystal between two substrates and there is no special treatment of the substrates, as is the case of our experiment, then for the director it's all the same which way to be aligned in the plane of the cell. But now if you tilt the top surface with respect to the bottom, then this degeneracy disappears because there is, generally speaking, a splay of the director, and this splay is not appearing only when the director is perpendicular to the gradient of the thickness. And now if you have the foot of the tectoid, which is an elongated thing that is at the bottom plate, that fixes the director at the bottom along this axis, but the tilt wants to realign it along the perpendicular axis, and you have a twist. So, and a simple estimate shows that it would happen when the twist constant is much smaller than the splay constant, and that's exactly what we know happens in the systems of harmonic type. So since it was very difficult to observe these three-dimensional structures of tectoids since they are distorted, and we wanted to explore how the defects will behave during the phase transition from the isotopic phase to the nematic phase, we decided to make the system two-dimensional. And in 2 dimensions, what we hope to see is to see how different tectoids with different initial orientation of the director would coalesce and whether they would produce topological defects as the result of this coalescence. The model is well known. It's the so-called Kibble mechanism of formation of topological defects. It was proposed in '76 to explain the formation of cosmic strings. And again, as I said, that in Lie crystals, in principle, you have a totally different mechanism associated with the surface anchoring that shows the topological defects in each and every droplet. But it was still of interest to see how the two-dimensional lyotropic harmonic Lie crystal would behave from the point of view of Kibble mechanism. The advantage of using this material is that you have a very broad range of coexisting nematic and isotropic phase. It's tens of degrees. So within this coexisting range, you can fix the temperature, and the amount of isotropic and nematic phase would be fixed. And so you can study in details what's going on with the nuclei and what's going on with the defects. And as already mentioned, the defects show the nuclei show up as tectoids, but now these tectoids are two-dimensional tectoids. So there is no change in the director of the director along the perpendicular axis. And we can use so-called pole scope, which immediately gives you the map of the director field in the Lie crystal. So these bars are nothing else but the distribution of the director that converges at the two-point defects at the poles of this formation. So here's the bigger sample. So what you see is the appearance of the nematic germs, nematic nuclei, and then they start to coalesce. And what is shown here is the result of two domains coalescing and forming a topological defect, a disconation of strength -1/2, right in the center. And so it's indeed very similar to the Kibble mechanism. Then you can continue the experiment further and further, and you would observe that not only the tectoids with just one defect might form, you might observe tectoids with two defects. What is interesting is that there is a certain relationship between the number of topological defects trapped inside this domain and the number of cusps at the surface. And each cusp contains a point defect at the interface between the nematic phase and the isotopic phase. And you might see that these cusps are of two different types. We call these positive cusps, and these are negative cusps, depending on whether the isotopic phase protrudes inside the domain or whether the nematic phase kind of reaches out. And sometimes the number of differently oriented nematic tectoids is so large that you can manage to trap configurations of the director that are equivalent to disconations of strength +1 or -1. And here you see a +1 disconation that shrinks. But then once the core becomes really small, you see that the line splits into two defects of strengths 1/2 each. And qualitatively, it tells you that when there is a large core of isotropic phase in this disconation, then it's from the point of view of the interfacial tension between the isotropic phase in the center and the nematic phase outside, it's better to keep just one core to minimize the interfacial energy. But when the core shrinks, then it is the elasticity of the director field outside and between the two half disconation that prevails, and it's better for the disconation to split because the elastic energy of disconation is proportional to the square of the Winding number or topological strength. Similar things for a disconation of -1 topological charge. This is an example when you go with the phase transition in the opposite direction. You start with the nematic phase and you hit the sample into the biphasic region, and you see that the isotropic phase nucleates at the core of the defect and then starts to grow. But the growth is not associated that much with the elastic properties of the disconation. It's mostly the condition of at which temperature in the biphasic region you find yourself, because the typical size of the core goes as a square root of the characteristic temperature at which you are located. A very interesting feature is that the core, the distance over which the properties of the liquid crystal change, and at which the liquid crystal, if you wish, melts and acquires a more complex configuration, as was shown by Slukin and others. In this regime, you have biaxial nematic phase, effectively. So it's interesting that in the case of chromonics, the scale over which these changes take place are much larger than molecular scale typically observed in the thermotropic liquid crystal. And apparently, it's associated with the fact that in this case, the so-called B constant in the expansion of Landau-Dejean is very small, which explains very large radius of the disconation. So ideally, it would be great if we would predict the shapes of each and every domain by taking into account the surface tension, the anisotropy of the surface tension, and the elasticity. And apparently, in this case, the three things are approximately of the same order, because we clearly see non-spherical shapes. Unfortunately, such a problem is not known to be solved. There are particular examples in Epifanio's book, examples presented by Rudnik and Brinsma and others. And the problem is extremely challenging. So we decided as the first step just to consider what would happen if we would freeze the director field and then create a blob of the isotropic phase and say that, okay, minimize the interfacial energy that takes into account that the surface tension in for different orientations of the director is different, and what would happen. And this is nothing else but the well-known Wolf construction that is used to predict the shape of crystals. The only difference is that our crystal is not uniform. It has this disconation distribution. And according to the Wolf construction, if you know the polar plot of the surface tension, you can reconstruct the shape of the crystal. And this is precisely what we do for our defects. So if the disconation has the topological charge -1, then you have 4 points where the director is perpendicular to the interface. But the equilibrium alignment is tangential. So that means that in these points, you would have a maximum of the surface tension. And the surface tension in polar plot is simply the distance from the center to the to this point. For tangential orientation, the surface tension is much smaller, and this distance is much smaller. So then if you know the polar plot of the surface tension, you can reconstruct the shape because the shape is nothing else but the pedal of the polar plot. And here are some examples for different disconations. Here is disconation -1/2, and this is how the isotropic core of this disconation would look like. Now, it turns out that the shape might form cusps and ears, which correspond to non-physical orientations of the nematic isotropic interface. And since we, in this simplified model, we know everything exactly and analytically, we can find out the condition for which you would have a shape with cusps and missing orientations. And this condition is written here for different m. M is just the strength of the disconation. It turns out that for 1/2 disconations, this condition is never fulfilled. So the interface in 1/2 disconation always has all the possible orientations. For the destination of -1/2, you might have 3 cusps, or you might have the shape that is totally round and regular. And here I just show the example. It depends on the strength of the surface anchoring. If the surface anchoring is kind of weak, then the shape of the non-trivial tectoid would be more or less round. But as you increase the penalty for bad orientation of the director, then the shape acquires this missing orientations. It simply doesn't want to be around the badly oriented director. Of course, the calculations are the same for positive and negative tectoids. It doesn't matter from which side you have the pneumatic phase. Peter, how much time do we have?
Well, 7 minutes.
7 minutes. Great. So what did we learn is that in lyotropic chromonic liquid crystals, we have much richer spectrum of interplay between the surface energies and the elastic energies. And unfortunately, even experimentally, we don't know much about these quantities. We don't know much about the typical lengths of the aggregates and how it changes with temperature or concentration. So we might think that future exploration will bring some interesting results. And finally, I will just briefly talk about colloids. So it's the inverted problem. You have a particle that is inside the liquid crystal. And we often use the word colloid. Colloid comes, according to modern definitions, for the situation when the particle is sufficiently small not to sink to the bottom of the container in which it is located, but to kind of hang up, levitate a little bit in the bulk, because such a small particle is subject to Brownian motion. And if this Brownian motion is capable to keep the particle at the typical z-coordinate that is comparable to the size of the particle, we call such a particle a colloid. So typically, a colloid is something that is smaller than 1 micrometer. So what would happen if you have a liquid crystal? Turns out, and this is the slide that summarizes the work on colloidal interactions between particles in the liquid crystal medium through director distortions. These interactions are long range and lead to anisotropic forces that create chains of droplets. But if you consider what would happen with these director distortions when there is a boundary, you would realize that the director distortions would help the particle to levitate in the bulk, because whenever you want to bring the particle closer to the surface, these director distortions will be enhanced. And you can calculate the deterministic position that would be the balance of the gravity and repulsive elastic forces. And surprisingly, you would find that this coordinate grows with the size of the particle. It's totally opposite to the case of normal colloids in isotopic fluids. And the example here shows that bigger particles levitate even better than smaller particles. And here you see just that the image was taken for the vertical cross-section of the cell. So this is just the same, just more quantitative results. So even if you take the very first step in trying to understand the colloidal particles that are placed in a liquid crystal as opposed to the isotopic fluid, you immediately see that there is a whole new physics here that is often not that intuitively clear. And I would like to just skip one of the things that is probably not essential here, but tell you that once you have these levitating forces, first of all, you can think of using them to help in self-assembly of three-dimensional things. Because whenever we are talking about self-assembly, people often forget to realize that as you self-assemble or directionally assemble something small into something bigger, then sooner or later gravity will switch the force, and this thing will drop to the bottom of the container. In liquid crystal, we might hope that with the help of this elastic levitation, we can keep the things in the volume of the system, and also it helps to explore some dynamics. And I would like to finish with the discussion, brief discussion of electrophoresis. So electrophoresis is a very simple thing, if you don't go into the details of it. So you have a charged particle, and it's in the isotopic fluid, and you apply electric field, and the system is electroneutral in general, but the fact that the charge of one polarity is sitting on this particle, and the other charges, counter ions, are floating in the fluid, leads to the motion of the particle in the applied electric field. And this velocity is proportional to the electric field, so it's a DC effect, very well known. So, and in liquid crystals, it turns out that, again, you just do one simple thing. You change the temperature, and your fluid becomes a liquid crystal. And it turns out that electrophoresis dramatically changes. Now, not only you have the motion of the particle parallel or anti-parallel, depending on the charge, to the applied electric field, and the electric field is shown here, but you also have a motion that is perpendicular to the applied electric field. And this motion is proportional to the velocity of it is proportional to the square of the electric field. So you immediately have an opportunity to use an AC field to drive the particle, and that is an important thing because, for example, if you would like to create some steady flows, electrophoretic flows, you cannot use DC for that purpose. You can only use AC field, and the liquid crystal allows you to do that. I wouldn't go through the proof of this quadratic. It's just the illustration in this movie that the field here is alternating. It can be sinusoidal, it can be sawtooth profile or other profile, and the particle moves in the direction perpendicular to the field. Since you can play with the director, you can arrange the director in different configurations and send this particle not just into the straight trajectory. You can force them go around, or essentially go from any point in three-dimensional space to any other point in three-dimensional space if you play with these two components correctly. And so what's the mechanism? The mechanism is in the fact that the sphere distorts the director around itself, and these distortions break the symmetry of the medium. In the simplest case, when you have a point defect that kind of compensates the radial configuration about the sphere itself, when you apply electric field, you switch ions into motion, and ions move in a fluid that is anisotropic. And obviously, the mobilities of ions in this portion of space and in this portion of space is different. And the non-compensated motion of ions around the sphere leads to propulsion of the sphere. Okay, this is just the mechanism, but here is the experimental proof that whenever you apply electric field to the sphere in the liquid crystal with this dipolar configuration, the motion of ions really occurs, and it is not compensated. Here you see the trajectories of ions around the particles that do not have the symmetry with respect to the horizontal plane, but do not have the symmetry with respect to the vertical plane, and this is what forces the particle to move. Huh?
How do you measure those trajectories?
We just apply electric field and then make zillions of photographs of the things, and then there is a special technique that allows us to connect the images.
You actually see the charges?
No, we see the motion of fluid through the fluorescent dye that is added to the things, but then we change the concentration of ions. And so what did we learn from this? That again, a simple thing. You just replace the isotopic fluid with a liquid crystal, introduce some anisotropy in the system, and you see some wonderful things. One of those things is nonlinear electrophoresis. And that is the end of my presentation. So I will remind you that I was trying to explain different situations in which the bulk elasticity of the liquid crystal competes with the surface energy of the liquid crystal, and that leads to a number of interesting situations, from formation of topological defects in each and every droplet of the liquid crystal that correspond to the equilibrium state of the system, to division of droplets, and in the case of chromonic liquid crystals, it's unusual elasticity, and also lots of interest in scenarios of phase transition from the isotropic phase to the nematic phase and back. And colloids and liquid crystals is extremely rich field. Even at the level of statics, you have levitation of particles in the bulk, and especially in terms of dynamics, because anisotropic properties of liquid crystals enable many things that you wouldn't see in regular fluids. And I wouldn't finish this without acknowledging that most of the experimental results were done by people currently working in the group. At the top are the graduate students, and Sergei Stoyanovsky and Luana Tortora are two doctors working in the group. And I enjoy collaboration when I started liquid crystals with Grigory Volovic, and then Maurice Clement taught me a lot about defects in them. Thank you very much for your attention.
Well, thank you for the beautiful talk, Oleg. I think in the interest of time, we'll break now and defer questions again for private discussions. And now we break for lunch, and